In this video, we'll review some practice problems identifying whether functions are injective, surjective, bijective, or neither. So for the first problem, we have our function, which is the floor function. So we take a real number, that's the domain, the reals, and the codomain is the integer. And the floor function takes the number x and it maps it to the largest integer less than or equal to x. So the first question is it an injective function? And recall, for an injective function, everything in the domain must map to a unique point in the codomain. And injective, we're going to say no, because we can think of 2 points in the domain that map to the same point in the codomain. So just consider if we just had the real numbers 1.5 and 1.6. So they are both distinct. They're not the same number, but they both map to 1. So that is a counterexample. So this function, the floor function, is not injective. And in fact, we have the whole segment of the real line. So we have infinitely many points mapping to the same integer. So it's not injective. Now let's see if it's surjective. And for surjective, we just have to show that every point in the codomain, so that's the integers, has a point mapping to it. And it turns out that, yes, it is surjective, and the way that we can convince ourselves of this is we're going to say for any point, so for any integer, we know there is a point in the domain mapping to it, and that's precisely itself. So the floor function will just map an integer to itself. And that means that for any point in the codomain Z, it will just map to itself. So yes, it is surjective. So we found for every point in the codomain, a point in the domain mapping to it, and it just happens to be itself, and that's just because the integers are a subset of the reals also. And because it is not injective, it cannot be bijective, because it would have to be both injective and surjective to be bijective. Let's consider another problem. So in this problem, we have our function f going from the integers to the reals, and f of x is equal to x divided by 3. So we want to know if this function is injective, surjective, bijective, or neither. So first, let's consider if it's injective. And remember that a function is injective if every point in the domain maps to a unique point in the codomain. Now, for this function, it is injective. And let's consider what happens when we consider two distinct points. So let x and y be two distinct integers, and by distinct we mean x does not equal to y, but they map to the same point under f, so that means f of x is equal to f of y. Well, if they map to the same point, we know that x divided by 3 has to equal y divided by 3, because that's the definition of the function that we have. And this would just imply that x equals y. So here we can see that if 2 points map to the same point in the codomain, that they're actually equal under f. So that means that they're equal to y, so that means that each point maps to unique point in the codomain. Okay, so it's injective. And if we were being more formal, we could just say, oh, we've derived the contradiction, so that would also settle it. But now for surjective, so to show that it's surjective, we would have to show that for every point in the real, so every point in the codomain, we would have an integer that is mapping to it. So is it surjective? And we can say no for this because there are some real integers that aren't rational. So for example, pi is irrational. It can't be expressed. So pi is in the reals and pi is irrational, so we can't express it as a ratio of an integer divided by 3, and there does not exist any no integer that we can divide by 3 that can equal pi. So this means there's no integer, there's no point in the domain that can map to pi. So it's not surjective. We just gave that as a counterexample, and there's many others. You can pick your favorite. And because it's not surjective, it is not bijective. Now let's consider a third example. So now we have a function mapping from the Cartesian product of the non-negative integers to the reals, and our function fmn will take the maximum of m and n. So we'll take, given a pair of integers or non-negative integers, it will return the maximum of those two integers. So the first question is this function injective? So by that we have to think about does every pair of integers map to a unique point in the reals? So is it injective? And we can say no, because we can come up with many ordered pairs that will map to the same point in the real. So for example, if I have f of 5, 5, that will map to 5. And if I have f of 1, 5, that will map to 5. And if I have f of 5, 4, that will map to 5. So you can see we've just given many different points, the points 5, 5, 1, 5, 5, 4, that all map to the same point in the codomain. So it is not injective. We just gave 3 counterexamples. So now let's think about surjective. So for the function to be surjective, that means for every point in the codomain, so for every real number, we need to have a point in the domain, so that's the cross product of the integers, that can generate it. And this is going to be absolutely no also. It's not surjective, and we can think of many counterexamples because, for example, when you're taking the maximum of 2 integers, it has to be an integer. So any number in the reals that is not an integer is not going to have anything in the domain mapping to it. So for example, point 1.75 cannot be the maximum of 2 integers, or 2.75, and so forth. So anything that is not an integer will not have anything mapping to it. So it is not surjective. And since it's neither injective nor surjective, it can't be bijective. So the answer for this one is neither. So neither in this case. And we can be more formal with the surjective, but for right now, it's fine just to say, well, we can generate many points that are in the reals such that they could not be the max. Of two integers. This would only map to the integers, is the takeaway there. There's many counterexamples for that. In this last problem, let's consider a function mapping the non-negative integers to the non-negative integers. But in this case, we have to consider cases. So if n is odd, it maps to n minus 1, and if it's even to n plus 1. So we want to consider if this function is injective, surjective, bijective, or neither. So first, let's consider injective. My claim is that it is injective, and let's just consider how this can be. So we're going to let's consider x and y, non-negative integers that are distinct, that are not equal to each other, such that they map to the same point under f in the codomain under f. So that's what we're considering those. So if x and y map to the same point in the codomain, they must have had the same parity, so they must have both been odd or both been even, because f changes their parity from odd to even and even to odd. So we have to consider each of those cases. So the first case is if x and y were both odd. Then if that's the case, then f of x equals f of y implies that x minus 1 equals y minus 1. But that just implies that x equals y. So if they're both odd and mapping to the same point in the codomain, then they had to have been equal. Now let's see if it's also the case if they're both even. So if both x and y are even, then they're both mapping to f of x equals f of y, which implies that x plus 1 equals y plus 1, which also implies that x equals y. So if they map to the same point, they had to have had the same parity, so either both odd or both even. And in either of those cases, if they're mapping to the same integer in the codomain under f, they're indeed not distinct. They're the same integer in the domain. Now let's consider whether it's surjective or not. And my claim is that this function is surjective. But in order to show this, we have to show that every point in the codomain, so every integer must have an integer mapping to it. So we do have to break this down into cases again. So let's consider if this point in the codomain is odd. So let's b in n and b is odd. Now we have to see what point would have to be mapping to it. So if b is an integer in the codomain and it's odd, then we know that an even integer had to be mapping to it. So that means we would have that f of b minus 1 would equal b, because b minus 1 would be even, and f takes an even integer and adds 1 to it, and we know that b minus 1 would be in the domain. So that's, we found for every odd non-negative integer, we found an even integer in the domain mapping to it. And now we just have to make a similar argument for b, and b is even. We have to figure it out. So b is even, that means it had to have an odd integer mapping to it because f is changing the parity. So let's just think about what that would be. So f takes its argument and subtracts 1. So f of b plus 1 would be equal to b, because b plus 1 would be odd, and f subtracts 1 from odd, and b plus 1 would be in the non-negative integers in this case. So in that case, we can see that for any element in the codomain, whether it's even or odd, we found a element in the domain mapping to it. And since it's surjective and injective, this function is also bijective.